Mr. Samms?
Yep.
Like, what are you doing?
Playing with the syringe.
A syringe? Like,
Yeah.
do you have like a drug problem, or
No,
what are you doing
I
with
don't
a syringe?
have a drug problem. Just playing with it, because you can learn a lot about gases from just playing with the syringe. See, look at this. See, there's nothing in here, right? Little tiny bit of gas.
Yeah, yeah.
Okay, I pull this out, and the pressure is really, really low in there. You know how I know it's low?
I don't know.
Because the atmosphere pushes it back in.
Very cool,
Isn't that
Mr.
neat?
Samms.
Yeah.
You're like a Tinkerband.
And I can push this down, but I can't push it all the way down because
Really?
I can only compress it so far. And then,
Oh.
see, I let
Yeah,
the whole
you let
pressure
gas
out.
out.
Here, I'm going to let it push
Oh,
it.
should we do it again? All right, let me
Well, I'm
zoom
going
in.
to let it push the plunger back at itself.
Oh, nice.
Or you can just, let it go there. But yeah, you can learn a lot about cool things about volume and pressure with gases and just playing around with the syringe. So I just, like to fidget with things and play with stuff.
Okay.
You know,
So
I'm
what are we going
kinda-
to talk about today?
Kind of wiggly. We're going to talk about gases and how they work in terms of pressure and volume and temperature and things like that.
Cool.
Mr. Samms, you sure like to play with things.
I know, I get bored and fidgety.
Yeah, well, we learned what were you kind of learning from there?
Well, I've got a gas in that tube,
Yeah.
and if I seal up the end and I push on it, I can compress that gas.
Yeah.
And it'll increase the pressure.
You're like trying to see how much pressure you
changes
could
the,
hold.
Right, changes,
Yeah.
and I change the volume doing that.
That's cool.
If I don't have the end closed, if I open it up, I change the number of molecules that are in there.
Do you turn the volume up? Like it's talking really loud?
Not that kind of volume.
Oh, what kind of
The
volume?
amount of space that it takes up.
Oh, volume is space that
Yeah.
takes up. Oh, I see. Okay, all right. So, hey guys, today what we want to do is we're going to talk about the properties of gases. Yeah, pretty short little podcast, I think. All right, take it up. Introduction to gases. Let's kind of get ourselves the properties of gases.
Okay.
These are our kind of topics for today. All right, first thing that you were playing with, Mr. Sands, we
Yeah.
learned that gases are
Compressible.
compressible. Now, what does compressible mean?
Basically, if you, like you can see in the picture
Oh, yeah,
here,
cool
if
picture
you,
right here.
if you shrink the volume of the container that they're in, you can actually push those gas molecules closer and closer together because there's a lot of empty space between gas molecules.
Yeah, gases are very, very spread apart.
Mm-hmm.
This picture, in fact, over here, this picture illustrates that they're apart, but actually they're much further apart than this.
Oh, yeah.
This is way distorted in terms of the picture. So since they're so spread apart, you can compress a gas.
Right, but solids and liquids, not so much.
Yeah. All right. So compressibility is the definition here is how much the volume of matter decreases with pressure. So that's kind of what we're talking about. So it's compressible. So that's pretty interesting. All right. Now, there are four things that we can measure when we talk about a gas. There's four variables, as I've said here
Yep,
in the
well, we just
podcast.
talked about two of them.
Yeah, which were what?
Volume and pressure.
Pressure. Okay, so let's take a look. Pressure, you already said. I'll
Right.
just throw it up here. And the second thing we can do is
volume.
And volume can be illustrated by this cool picture right here where we have a guy with a weather balloon.
Yeah, now in terms of pressure, in Unit 6 we talked about different units that pressure is measured in and how
Right.
we convert those. So you're just going to apply what you learned there to this.
Right. Yeah, let's actually do a little review. That's
Yeah.
good thought. Well, let's do it at the end because we'll have them all
Okay.
together. Okay, and then the third one is temperature, and this
okay.
is a picture, by the way, of the temperatures, today's high temperatures in the Earth. So actually, it's February 9th, 2007, but whatever. Today is February 1,
February 1,
of
2010.
And so, yeah, you can see the temperatures here in February of this date right here. But, well, it's just a few years ago. And you can see it's quite hot here. And then, of course, way up here, it's really, really cold. So temperature. And lastly, the moles of a gas.
Right.
What's that mean, moles of a
That's
gas?
the actual number of particles that we're dealing with
Yeah.
of gas molecules.
So, yeah, if you were to
Or
1,
atoms.
2, 3, 4, 5, start
Yeah.
counting them, the little balls.
More like 10 to the power of 20 and up.
Yeah, because
is what we'll be dealing
because
with.
we're using lots of them. Now let's just kind of do a quick review. What are the units that we're going to be working with when we talk about these different variables?
Typically in here we're going to be talking in units of atmospheres, ATM.
Atmospheres.
But you may also see millimeters of mercury, which is also the same thing as a torr. And you may also encounter a kilopascal. And all the
Occasionally, yeah, we'll see a kPa.
And that's
Okay.
actually becoming more and more the case in
Yeah.
more textbooks.
We'll talk about that, and we'll put some some call-outs
and we've
on
done
that.
conversions on that in Unit 6.
Now volume, we measure volume using what?
Liters is
Okay.
what we'll be dealing with, but you may also encounter it in milliliters.
All right, you see. You actually, in some of the problems in our packet, I think you'll even some that are sometimes like in gallons and stuff.
Yeah.
Although very rarely.
Yeah.
Okay. Temperature. Now, temperature's an interesting one.
Right. Now, usually we measure temperatures in Celsius, but when we're dealing with gas laws, you always have to convert it to Kelvin. Always, 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 always,
How do you
always,
always?
always, always, always.
Okay, always.
What are the temperature units?
Kelvin.
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 Always.
Kelvin.
Never
Kelvin.
Celsius, ever.
How do you convert from Celsius to Kelvin, Mr. Samms?
Add 273.
So 270. So
That's
you
it.
take Celsius plus 273 is K.
Do not do any math in Celsius.
Never do math in Celsius?
Well, unless you're just adding 273. But never do
Yeah,
your
yeah,
calculations for gas laws, but we're going to talk about in the next lesson, in Celsius. Has to be in Kelvin.
It's got to be in Kelvin. That's my new voice.
I like it.
Do you?
It's
Kind of,
well,
whatever his
different.
What's his name? Kermit the Frog.
That's not Kermit the Frog.
Oh, whatever.
No.
It's no. All right. Moles of a gas.
This is Kermit the Frog.
Oh, you're bad. Oh, you're good.
Yeah, I have small children. We watch a lot of Sesame Street. And
Moles
a
of
lot
a
Muppets.
gas. Moles of a gas. That's just moles.
Yeah. Yeah, moles.
The symbol for moles is MOL.
Yeah.
As opposed to MOLE. Okay, that's pretty
I'm
easy.
surprised I got the Kermit voice out. I'm
You're
only about a third of the way done with my
amazing
coffee
with the
this morning.
Kermit voice. All right. Now, there's something we also need to talk about is that gas particles are actually not affected by attractive forces. What in blazes do I mean by that, Mr. Sams?
Basically, we have to assume that the little particles of gas molecules, they don't actually attract or repel each other.
So if I get two gas particles right here and
Yeah.
here, there's no attractive force between them.
Now, in reality, there is, but for our purposes in
Yes.
studying gases, we're going to assume that there isn't.
So we're
Okay.
making an assumption.
We are, and it's a fair assumption because
Yeah.
there is attractive force, but in the conditions that we're going to be dealing with gases, it doesn't really matter all that much.
So guys, if I have an oxygen molecule here, and I have an oxygen molecule here, represented by my fists, then they don't connect together. When they connect together, that's attractive forces.
And they don't repel either.
And they don't repel either. That's correct.
Yeah, we're just assuming that they're not affected by each
All
other
right.
at all.
Couple things. I think these are just sort of intuitive. Why does pressure go up when you pump up a bicycle tire? So let's just kind of deal with some.
Yeah.
So you probably pumped up a bicycle tire, or maybe pumped up a car tire of some variety. So you got the guy pumping up his bicycle.
Yeah.
Why does the pressure go up?
Well, we're adding more molecules of gas.
Yes.
We're introducing
More
particles,
So
more
if
moles of gas.
If this is my bicycle tire, a cross section of it, if maybe this is how many molecules are in the bicycle tire, but if you have the pump, this is a pump right here, and you add more, well, guess what? There's more of them in there.
Yep.
And what's pressure caused by?
Collisions of the molecules with the side of the container.
So as these molecules move and hit, you've
Yeah.
got more molecules
more molecules,
hitting,
more collisions, more pressure.
collisions, more pressure.
Yep.
That's exactly right. All right. Let's take a look at this one. Here's an aerosol can. A little interesting question here. Why does an aerosol can work?
Well, things in nature go from high to low.
All right, high to low.
Energy goes from high energy to low energy, or high
Hot to
temperature,
cold,
hot to
or
cold,
hot-
right. Well, gases move from areas of high pressure to areas of low pressure. So
Okay,
inside the can, we have gas at very, very high pressure.
So this is at high pressure
Yep.
already.
When
When you buy it.
Right, when you buy
Yeah.
it. When you push the nozzle down, it provides an outlet for those molecules to get out, and the molecules go, hey, pressure's less on the outside. I'm going out because that's what I do, because I go from high to low.
So here we have low pressure, and here we have high pressure.
Right.
Yeah, and it's pumped in there, if you will, when they manufacture it. Right. Okay. All right, let's do another question, Mr. Sams.
Okay.
I'll see if you can start and stump you here. Why does the pressure in a can increase when you push on the plunger?
Well, I don't know. You stumped me. That's a tough one.
All right, so here we've got a plunger. It's kind of like this is what you were doing at the beginning
Right,
of the
with the-
podcast
with the syringe.
with the syringe deal, and you were pushing down on it, and the pressure was like getting too. You could hardly hold it
Right,
down.
there comes a point where I can't push it down any further because the pressure pushing back is too much. So all I'm doing when I do this is I'm pushing the molecules closer and closer together.
All
If
right.
they're closer together, there's more of a chance. If this chamber is smaller, I guess I should say, there's more of a chance for
Right.
collisions with the outside, and the pressure goes up.
Right, yeah, and more options to hit the sides.
Mm-hmm.
There's less side to deal with.
Right.
So the pressure is going to go up. Mr. Sam, let's finish with just one little interesting thing here.
Okay.
Why does the sealed can explode when heated? Here's what happened. There's a car right here, and you, take a look at the broken window of this car. Think it was hit by a hailstorm? Kids playing ball, gunshots. Nope, nope, and nope. If you click on the photo to enlarge, which I've already done, you'll see the culprit, a pressurized can. This pressurized can got heated up. It was a hot day in the summer probably, and it got hot. So what happens when you heat up a can? That's pressurized.
Yeah, well, if you heat them up, if we think in terms of kinetic molecular theory, those molecules move faster. And if those molecules move faster, there's more collisions, and they're hitting the wall with a greater velocity, meaning more pressure inside the can.
So if the pressure goes up inside of a can and goes way up, it can explode.
Yeah,
which is-
eventually it's not going to be able to hold the amount of pressure in there, and it's going to fail at its weakest point.
You've probably, guys, seen the warning labels on aerosol
Do
cans.
not incinerate. Do
not
not throw
incinerate.
into fire. Do not let it go above 120 degrees.
And guess what? They did that. They had it inside a car, and you get 120 degrees inside of a car on a hot summer day, and that's what did it. It exploded, and it exploded the back of this car window. That's kind of cool.
That is.
Wow. Okay, hey
scary.
guys, the very quick podcast, just a quick introduction to gases. We're talking about how's
I don't remember. Probably go back to your French, Russian, German
all right,
accent.
they're going to be done with the gases because the gases are done.
Yeah, that one.
Yes, okay. All right, we'll see you in gases. Cheers.